This is Inorganic Chemistry, Chapter 5, Transition Metals. In this lesson we're going to look at pages 171 to 174, the oxidation states of transition metals, and page 175, amine complexes of transition metals. So here on page 171 we have the three series of transition metals, first, second, and third, and all of their oxidation states. So in the first transition series we have scandium through zinc. The second transition series is yttrium through to cadmium, and the third transition series is lanthanum through to mercury.
The zero oxidation state represents the element where the number of electrons is equal to the number of protons.
The elements are neutral, and these are the ground state electron configurations I have highlighted. The vertical leftmost column lists the possible oxidation states for the transition elements. If you look at group 3b, scandium, yttrium, and lanthanum, you'll notice that the only oxidation state that we see is +3. So they have fixed oxidation numbers. Go to the other side of the table, the right-hand side. Notice in group 2b we have zinc +2, cadmium +2, and mercury +1 or 2. So almost always +2. In the case of group 1b, we have copper, can be 1 or 2, silver, only +1, and gold, 1 or 3. Other than those, we see that most of the transition metals have multiple oxidation states. The highlighted values are the most stable, or at least the most common, oxidation states of the transition metals. Notice the group numbers. We described this previously. The group numbers represent the highest possible oxidation state for any member of the group. In group 3b, of course, you're only +3. In group 4b, 4 is the highest oxidation state of any member in the group, titanium in this case. In group 5b, vanadium's highest oxidation state is +5. In group 6b, chromium's highest oxidation state is +6. This is also true for molybdenum and tungsten beneath it. In group 7b, manganese highest oxidation state is 7. Also true for technetium. Also true for rhenium. We get to group 8b. Well, it applies somewhat. Ruthenium has a +8 oxidation state, and so does osmium. And beyond that, there's not much of a fit. The rule kind of falls apart. I'm going to scroll to the bottom here. I want to point out to you that the first transition series metals form ionic compounds that dissolve in water, giving free ions, free cations. So we can have a chromium 3, iron 3, cobalt 2, etc. They'd be solvated by water, otherwise free. But the second and third transition series metals, their ions are polyatomic ions, typically oxyanions like molybdate and tungstate. Please take a look at page 172 with me. Here we have the third period, first transition series metals and their cations. Now, in the middle column we have the reduction reaction of one of their cations going to the metal. In each case, reduction is occurring from cation to metal. In the third column we have the electrical potential, the voltage involved in this reaction. So as for example in the case of scandium, the potential is -2.08 volts. Recall that negative potential means that it's unfavorable. We would have to apply at least 2.08 volts or greater to force scandium plus 3 to accept 3 electrons and be reduced to scandium metal. And with the exception of copper, this is true in all cases, the reduction of the transition metal cations is unfavorable. Now these reactions are all reversible. We could take scandium metal and it would readily be oxidized, losing 3 electrons to form scandium plus 3. And the potential for that, it would be plus 2.08. Just change the sign from negative to positive if you reverse the reaction. So what this means is that most transition metals are reducing agents. So the metal will preferentially move in this direction, giving up electrons, and reduce whatever it's reacting with. They'll do that in the environment because oxygen in the atmosphere is an oxidizer, or it'll do it with mineral acids, liberating hydrogen gas. So what's a mineral acid? Well, a mineral acid is an inorganic acid, as opposed to an organic acid like, say, acetic acid or citric acid or ascorbic acid, carbon-based acids. The inorganic acids are things like hydrochloric, hydrobromic, iodic, sulfuric, nitric, and so on. And because transition metals are characteristically reducing agents giving up electrons, we typically don't find transition metals in their elemental state naturally occurring. So for example, we would tend to see titanium as an oxide, as an ore, or sulfide of molybdenum, an oxide of tungsten, an oxide of iron, and so on. In fact, here's an image of copper, elemental copper found in a native or natural state, and here's iron in its native state. It's in an oxidized form when it's naturally found or naturally occurring. So copper and the 8 noble metals are the exceptions to the rule that transition metals are usually reducing agents. The noble metals are ruthenium and osmium, rhodium and iridium, palladium and platinum, silver and gold. If you look at a periodic table, they're easy to see. There's 8 of them: ruthenium and osmium, rhodium and iridium, palladium and platinum, silver and gold, all 8. Along with copper can be found in the elemental state. They're not particularly reactive. They're not reducing agents. Some years ago, a student in my class introduced me to a friend. She said, "I want to introduce you to someone I know, and his name is Mazikental H. Chapa." And she then explained that each letter corresponds to an element: magnesium, aluminum, zinc, I is for iron, C for cadmium, N for nickel, T for tin, L for lead. Mazikental. H for hydrogen, C for copper, H for mercury, A for silver, P for platinum, and A for gold. Mazikental H. Chapa. This is an abbreviated electrochemical series, easy to memorize. If we tag onto the front of that the elements lithium and potassium and barium and calcium and sodium, this person's formal name could be written as like Bacana Mazikental H. Chapa. Now, a generation ago, I wouldn't think twice about asking students to memorize that. It's certainly a handy and useful mnemonic, but times have changed, and I know students don't typically wish to invest in memorizing, so I'm not going to ask you that either, but it certainly is useful. Let's take a look at the next page, and we'll come back to this after. I'm going to skip right ahead to page 174. So here, in fact, is an abbreviated activity series of metals. Like Bacana, Mazicanto, H. Chapa. The activity series of metals. This is not a comprehensive list, but it's certainly a good list of the most common ones. The group from lithium down to sodium are indeed the most reactive of metals. Here are the metals, and they have very large negative reduction potentials. That is, it is very difficult to reduce the cation to the metal. In fact, these are such strong reducing agents. When you put these metals in water, they'll actually reduce water to hydrogen gas liberated. The next group, magnesium through lead, Mazicanto. These metals are moderately strong reducing agents. They won't typically react with water, but they will reduce hydrogen ion liberated from dilute mineral acids. And then we encounter hydrogen. Its redox potential is 0. This is the reference that everything else is compared to. And those elements that are below hydrogen on the activity series are typically noble metals. They are poor reducing agents. They do not react with mineral acids. They would require much stronger acids to oxidize them. For example, mixtures of nitric and sulfuric acid together make something called aqua regia, which is a very strong acid and can dissolve some of these elements like platinum and gold. With that in mind, let's return to page 172. And we'll say a little more about this. So there are the noble metals that resist oxidation. They are not good reducing agents. Here is gold ore in its native state. It exists as the element, and likewise here's silver ore. They're noble metals. And here's a photograph of those 8 noble metals: ruthenium and osmium, rhodium and iridium, palladium and platinum, silver and gold, and copper. Please take a look at page 173. Here we have a frost diagram of the first transition series, scandium through zinc. Now, scandium and zinc are not included because they only have one oxidation state, but for those elements that have more than one, they're listed here. Recall that the y-axis represents the energy of a given oxidation state. So a higher y-axis position means more reactive. So for example, titanium, its element with oxidation state 0, is quite reactive. It would like to be oxidized and give up 3 electrons and form its most stable oxidation state +3. So higher y-axis position means more reactive. Look at vanadium. Vanadium metal is a reducing agent. It'll readily give up 3 electrons, forming vanadium +3. At the same time, vanadium +5 is an oxidizer. It would readily gain 2 electrons and be reduced to vanadium 3. Look at chromium metal. Chromium metal is a reducing agent. It will readily give up 3 electrons to be oxidized to chromium 3. At the same time, chromium 6 is an oxidizer. It would readily gain 3 electrons to be reduced to chromium 3. How about manganese? Manganese 7 is a very strong oxidizer. It will gain 5 electrons to be reduced to manganese +2, whereas manganese metal is a reducing agent. It would lose 2 electrons to be oxidized to manganese +2. Copper is the exception. Notice that its native elemental state is the most stable state, and so copper +2 is an oxidizer and can gain electrons to form the element. Alright, so given that information, let's see if we can answer these problems. Problem number 4 says, given the preceding frost diagram, write the formula of A, the most common chloride salt of titanium. Well, titanium, we can see in this frost diagram, the most stable oxidation state is +3. And so the most common chloride would be titanium 3 chloride. The only sulfide of zinc. Recall that zinc only exists as +2, so its most common sulfide would be zinc sulfide, in which zinc has an oxidation state of +2, and sulfide, of course, is always -2. The most stable phosphate of iron. Well, what's the most stable oxidation state of iron? You can see here it's +2. And so the most stable phosphate of iron would be iron 2 phosphate. FePO4. Now phosphate has a charge of -3, so that'll be 2 of those and 3 of those, right? Fe plus 2, PO4 minus 3. Charges, oxidation states total 0. Problem number 6. State whether the following reactions will occur spontaneously at room temperature. If the reaction does occur, write a balanced equation for the reaction. If the reaction does not spontaneous, just state no reaction. So in the case of zinc reacting with water to evolve hydrogen gas, what do you think? Well, does zinc react with water? Let's flip back to our electrochemical series. Notice that zinc is below the active metals and it does not react with water. It would react with hydrogen ion but not water. And so in this first example we're going to say no reaction. We'll put zinc plus water at room temperature, no reaction. Okay, B. Mercury reacts with cold dilute nitric acid. A bit of a tricky one. Mercury plus nitric acid. If you look at the activity series on the next page, or if you recall, mercury is actually below hydrogen on the activity series. And so it should not, mercury metal would not be oxidized by hydrogen ion under normal conditions. So the direct answer here would be no. You'd say no reaction. However, if you recall in experiment number 7 we studied the chemistry of nitric acid, we learned that nitric acid is an oxidizer not just because of the hydrogen in the +1 oxidation state, but also because nitrogen is in its highest oxidation state, +5. And therefore nitric acid is actually an oxidizing acid. And if this nitric acid was not cold and dilute, but rather it was, say, room temperature and a little bit stronger, we would in fact find the nitric acid would dissolve mercury. But given the conditions here, cold dilute, we'll say no. The obvious answer is no. C, we have barium reacts with water. Barium plus water. If you recall, barium is one of the strongest reducing agents on the table, and it would indeed reduce water. In the process, water is reduced to hydrogen, and the metal hydroxide is precipitated. Is this balanced? Not so much. Let's put a 2 here and now we're good. So yes, indeed, barium is a strong reducing agent. Like sodium or potassium, it will reduce water to the metal hydroxide and liberate hydrogen. Calcium with conc HCl. Calcium is another strong reducing agent, reactive metal, and it certainly will reduce water to hydrogen and the metal hydroxide. So yes, that will react. Cadmium with dilute sulfuric acid. So cadmium and H2SO4. If you want to look at the activity series of metals, you see cadmium is above hydrogen on the activity series, and so in fact cadmium will react. It'll be oxidized to cadmium-2 by hydrogen ion. Now the reaction may be slow, but at least theoretically it should work. That'll be cadmium sulfate. Cadmium is only +2 and 2 hydrogens reduced to make hydrogen gas. Okay, F. Manganese 3 reacts with chromium 2 in solution. Manganese 3 and chromium 2. Will it react, and if so, what will it form? Let's take a look at the Frost diagrams for these. Manganese 3 is active as an oxidizer. It would like to gain an electron and go to +2. And chromium 2 will be active as a reducing agent, would like to give up an electron to go to +3. So that looks like a favorable reaction. So we'll form manganese 2 and chromium 3. When you have equations involving charges, the charges must balance as well as the mass. In this case, everything's balanced. So manganese 3 is gaining 1 electron to be reduced to manganese 2, and chromium 2 is being oxidized, is losing 1 electron to form chromium 3. G. Titanium 2 reacts with vanadium 5 in solution. Titanium 2 and vanadium 5. Will it react? Will they react? And if so, what will they form? Let's take a look at the Frost diagrams again. Titanium 2 and vanadium 5. Titanium 2 is a reducing agent. It would like to give up an electron and form titanium 3. Vanadium 5 is an oxidizer. It would like to gain electrons and form vanadium 3. So that looks like a favorable reaction. So titanium would prefer to exist as titanium 3, and vanadium 5 would prefer to exist as vanadium 3. So that looks correct, but I can see the charges aren't balanced. We have a charge of +7 on the left and +6 on the right. Let's see. Vanadium is going to gain 2 electrons, and titanium's only got 1 to give, so we'll need 2 titaniums, each giving an electron. And now the total charge on the left is 4, plus 5 is 9. This is 2 times 3 is 6, plus 3 is 9, and now it's balanced, charge and mass. And finally, H, copper 2 reacts with nickel in solution. That's nickel 0. Will that react? Well, let's take a look at the activity series. That is the Frost diagrams. Copper 2 is in fact an oxidizer. It would like to gain electrons and form copper 0. And nickel is in fact a reducing agent. It would like to give up 2 electrons. That looks like a match that will certainly work. So nickel will give up 2 electrons, forming nickel plus 2. Copper 2 will gain 2 electrons to form the element copper, and that reaction is balanced for charge and mass. Take a look at page 175. Amine complexes. This is the last piece of this lecture on transition metals. most of the representative metal hydroxides, by that we mean the A group metal hydroxides, and also transition metal hydroxides, are insoluble in water. So here's a representative metal hydroxide. It's quite insoluble. There are exceptions, of course, to group 1A metal hydroxides, lithium, sodium, potassium, rubidium, and so on. And a couple of the group 2A metal hydroxides are in fact soluble, but for the most part, most representative metal hydroxides are insoluble, and it is also true of most transition metal hydroxides. Now recall that some metal hydroxides are amphoteric. That is, they'll dissolve in a base or in an acid. For example, one we've looked at is aluminum hydroxide. In the presence of sodium hydroxide, the insoluble aluminum hydroxide actually redissolves, forming this soluble complex species. This would be tetrahydroxoaluminate ion. We'll call it a soluble hydroxyl complex. Now, ammonia is a base. If we put some ammonia in water, here's ammonia in water. It's a moderately strong base. It ionizes to some extent, producing ammonium ion and hydroxide ion. Typically, ammonia solutions of even some strength are not much more than pH 11, so the quantity of hydroxide is not all that great. So ammonia is a moderately weak base. It's pKb 4.8. It would not be expected to be able to produce a high enough concentration of hydroxide to produce enough hydroxide to dissolve insoluble amphoteric metal hydroxides, like in this reaction, to produce the hydroxyl complex. But several metal hydroxides do in fact dissolve in excess ammonia to form amine complexes. For example, copper 2 hydroxide with ammonia in fact dissolves the ammonia, but not as a soluble hydroxyl complex, but rather as an amine complex. The fact that it's charged makes it water soluble. So for example, here's calcium ion precipitates with hydroxide to produce calcium hydroxide insoluble, and the addition of excess hydroxide has no reaction, as expected. Copper 2, on the other hand, behaves a little differently. It will precipitate with hydroxide, forming copper 2 hydroxide, but it will redissolve. In fact, we need 2 moles of hydroxide, and it'll form this tetrahydroxocuprate complex, which is water soluble. And interestingly, copper, which precipitates with hydroxide to form copper 2 hydroxide, will in fact dissolve if we add ammonia. 6 moles of ammonia will form this hexaamine complex of ammonia and release 2 moles of hydroxide ion. Here we're seeing an amphoteric hydroxide dissolving in excess base. Here we're seeing an amphoteric hydroxide dissolving in excess amine. It's not because ammonia is a strong enough base to produce enough hydroxide. It's simply that ammonia binds very strongly with transition metals and it displaces the hydroxides. Cobalt 2 hydroxide reacts with 6 moles of ammonia to produce hexaamine cobalt 2 ion, which is water soluble, displacing 2 moles of hydroxide. Interestingly, all metal hydroxides that exhibit this behavior come from the 12 metals of the cobalt, nickel, copper, and zinc groups. Here they are: cobalt, nickel, copper, zinc, rhodium, palladium, silver, and cadmium, iridium, platinum, gold, and mercury all form these soluble amine complexes. Now, obviously, you're certainly not expected to memorize the combining ratios of amines to metals because they're not consistent. I don't see a particular pattern or a rationale for it. But given a problem like this, I think you could answer this. Let's give it a try. Write a balanced equation for the reaction of 6 moles of ammonia with each of the following. So since I've told you it's 6 moles of ammonia, you know the combining ratio. Au OH3, that's gold 3 hydroxide, plus 6 moles of ammonia produces an amine complex of gold. Here's gold with 6 amine groups. And what's the charge on this? Well, in this complex here, gold is plus 3, and so it's still plus 3, and releases 3 moles of hydroxide ion. Notice that the charges are balanced. The charge on the left is 0, and the charge on the right, the total charge, is also 0. Here's platinum 4 hydroxide plus 6 moles of ammonia goes to a complex with 6 moles of ammonia combined with platinum, and the charge on the platinum is plus 4 in both cases, and 4 hydroxide ions are released. And in fact, these equations are balanced for charge and mass. And that's it for this first lecture on transition metal oxidation states and amine complexes.